I'm Matt. I'm Matt Topol. And there we go. So I call this slide the "Why should you care what I have to say" slide. Um. So up until recently, I worked at Backend Research Systems, financial software, analysis, computational systems, and data distribution, and those types of distributed computational analytics. Recently, I had the distinction of being able to say that I literally wrote the book on Apache Arrow. I can say that because there's only one book, and it's the one I wrote. Which whoever asks the best question at the end when they get that, and they'll find it. But otherwise, the idea is, given if you have seen my book or otherwise, or don't know anything about it, the book itself is about Arrow in general. It talks about the entire Arrow format, how it works, why we use it, gets about the use cases, dives into Jupyter and Spark, and a whole bunch of things when using Apache Arrow. So the first thing I'm going to do is I'm going to give it just a quick primer on Apache Arrow, just in case anyone is here and only vaguely knows what it is, and just, I heard the term, I heard the word, and but isn't really sure of what it is or why I use it. I'm going to get a quick primer on that first. After that, kind of go and do why am I talking about using Go with it as opposed to Python or C++ or Java or any other languages. And then we'll go through a bunch of examples of actually using the Go, Arrow, and Parquet libraries. That will hopefully be interesting to you guys. If anything doesn't make sense, if you're confused by something, let me know. Stop me, please. Interactivity. So, quick primer on Apache Arrow. Arrow is a in-memory columnar format. The idea there is it's a high-performance design so that if you have data, tabular data in one system, and you want to get it to another system, you don't have to pay serialization costs. Because typically, when you have lots of different systems, you're dealing with, Cassandra or HBase, Pandas, like you have all these different systems, all these different tabular data formats, and anytime you want to get data from one to the other system, you have to serialize it or convert it from one format to another, and that costs time. And a number of years ago, people who originally co-created Arrow basically did the measurement of going, in a lot of systems, especially Hadoop at the time, almost 90% of the execution time was spent in serializing and deserializing data over and over again, as it went from system to system and crossed the wire and so on. So the idea of Arrow is that the data itself is the same format in memory as it is on the wire. There's no serialization cost or deserialization cost for the Arrow data as you pass it from system to system, but it's also highly efficient to operate on because it's column-oriented, and you get the benefit from, and if you're not sure what columnar or column-oriented is referring to, here's an example. So you can see on the top there you have a table of data. And this example is actually right out of my book. You have a table of data. On the left side, you have what is the average way most people would think about this table is you have essentially an array of structs where you have the data organized in that format. Instead, Arrow organizes things column at a time, all contiguous in memory. The end result being, instead of the array of structs, you have essentially struct of arrays. And what this gets you is better memory locality and better I/O, especially on other formats, such as, say, Parquet, and converting and interacting that way. So, for example, if you wanted to get, for that table in the previous slide, if you want to get all the archers in Europe for that table, you only need two of the columns, which means you only need two chunks of that memory, of that data to be in memory to get the answer. You don't need, whereas if you're in the row-oriented way, you need the entire table to get the answer. Not to mention, it makes it easier to optimize with vectorized operations, because vectorized operations require contiguous chunks of memory. If you want to get the mean of one column, Well, if you have an arrow record batch, you have an arrow array, your data is already contiguous, and it makes it very efficient and easy to leverage vectorized computational. And the arrow libraries, most of them will implement a lot of vectorized optimizations. Arrow is very polyglot. There is an implementation in C++, Go, Python, Java, R, MATLAB, Julia, probably a bunch of other languages I'm missing. So the benefit there is that you can write your service, your data, whatever you want, in whichever language you want, pass your data to another service of whatever language that has an arrow implementation, and you don't have to pay any conversion or serialization cost because they're both using the identical memory format. So that's kind of the quick primer on Arrow there. So why Go? Why am I talking about Go? Well, I picked up Go a number of years ago and found that I am really fond of it. It's very simple and easy to pick up. It is compiled language. So unlike, say, Python that's interpreting it, Go is going to be significantly faster and not dealing with, various things like the global interpreter lock that Python has, for example. It's compiled, you get machine code. Go also has a lot of really, really great built-in concurrency primitives. And because the binaries you produce with Go are, for the most part, very static binaries, is significantly easier to deploy something written in Go than in many other languages. Hence, it's something I really enjoy. Plus, I find the language a lot of fun to actually use, which is important. I enjoy it. I enjoy using it. So, this is the import path for the Go, Arrow, and Parquet libraries. The official repo, GitHub.com Apache Arrow repo has the implementations for the majority of the languages that supports. The Rust implementation is a separate repo. But then there's also a Parquet library in the Arrow repo that provides a PQ Arrow module to give very efficient interactivity between Arrow in memory and Parquet directly. So that in addition to having your low-level Parquet interactions, you can also get extremely easy Arrow to Parquet conversions that are efficient, that will take advantage of 0 copies whenever it can, and just reference the memory as is. So, let's start exploring the libraries and looking at some code. Before we look at the code, let's get some terminology out of the way. Because, especially if you're not familiar with Arrow in general, these are important to understand. Now, the primary smallest piece unit that you're going to talk about, you have Arrow arrays, which are effectively anywhere from 1 to 3 buffers of contiguous bytes, and some metadata that tells you what they mean. For example, those buffers are generally a bitmap containing what things are null in the array, where if the bit is not set in the corresponding index on the bitmap, it's null. If the bit is set, it's not null, it's valid. And then you'll have some quick things like the length, how many nulls are in the array, the data type, so on and so forth. Building on that, you have record batches, which are represented with the arrow.record interface, which is just a group of arrays that are all the same length, plus a schema that describes names, types, any metadata you want for those columns, and schema level metadata too if you want it. You can have chunked arrays, which is a sequence of arrays that you treat as one large array. And the benefit there is, say you're reading in a large amount of data. You're going to read in a chunk of data from your I/O, and then you're going to read in the next chunk, and you're like, okay, now what do I do? Well, okay, if I didn't know the whole size beforehand, I guess I need to reallocate a larger buffer and then copy it over. Or with a chunked array, you can just take that in the chunk you just did and treat it as one large array without having to copy it and reallocate and make new things. You can just treat it as a large array. So that's where the trunked arrays come in, which are then built up to become a table, which, like a record batch, is a group of arrays that have the same length. A table is a group of trunked arrays of the same length. So, for example, you can take a group of record batches and treat them as one large table. And the Arrow implementations interact with them in those ways to get the benefits and to optimize where it can. The key here is reducing copying. We're going to reduce the copying while optimizing on the processing. So let's get some simple examples. Simple example: build a single 64-bit integer array. You can see that we've got a memory default allocator. The allocator is an interface in the Arrow Go library. It has 3 simple methods: allocate, reallocate, free. The reason why it exists is so that you can control how and where the memory is coming from. The default allocator is just using Go's internal make a byte slice. The default allocator is just make a byte slice. When you allocate, it'll reallocate by making a new byte slice and copying, so on and so forth. But if you wanted to say, if you're going to be dealing with CGO, for example, you can use an allocator that allocates the memory using C instead of using the Go allocator, and then you're bypassing having to deal with Go's garbage collector if you need that extra bit of performance for how you want to handle the memory. The buffers, everything that handles the arrays, the buffers, the record batches, all of them are reference counted internally. So you can see that we defer a release on the builder, and then we append a value, we append a null, you can append a list of values. And the second argument is a slice of Boolean, where if you give it null, then nil, then everything is valid. If you give it the actual Boolean slice, then all the true are valid, and the false gets treated as null. So you can see the example on the bottom of the output would be here, where we set those 2 nulls in. And also notice that we defer and we release the array. Again, if you're just using the Go default allocator, it's not as important, but then you're tying yourself to the idea of no one's ever going to swap your allocator out. By using the release and defer release, not only are you allowing the ease of use of using other allocators, but it also means that you releasing the memory early and eagerly, so that Go's garbage collector can eagerly go, oh, no one's using this anymore, and then collect and recollect it if it needs to. So laugh, come on, one person, laugh. Okay, so all the objects, arrays, buffers, builders, tables, records, you have retain and release. Retain adds 1 to the reference counting, and release reduces 1 from the reference counting. And when it hits 0, it cleans up everything below it. So, for example, you saw we did a release on the array. The array has multiple buffers. So when the last release is called on the array, it will call release on buffers, which is important because you can have multiple arrays sharing the same buffers so that you can share data across multiple arrays, and it would have the appropriate ref count for it so that when one is done, it calls release, but it stays valid until the other one calls it, so on and so forth. So you saw the int64 builder earlier. There's a builder for all the different types. In this case, now things get a little bit more complex when you're building any of the nested types. When you're building a record batch, you can, because there's a record builder, there's a struct builder, there's a list builder to build the different types, the nested complex types. You can see here, we make a struct type, defining our struct, and you have a list of fields. We have our data, we have our struct builder. Notice that we don't have to separately call release on the individual field builders. We only have to release the struct builder at the end. Now, if you're going to pass ownership around, if something else is going to take ownership of it, that's when you call release before you pass it off. And I'll show you that later. So you can see here, we grab the different builders for each column. We whip through our data and append to our builders. We append a null to the struct array itself. And then we can just call it new struct array and get our data. Then we can print it out and do whatever we want with it. So struct arrays just is a builder with a struct builder, just a collection of other builders for each field. Same thing goes for a record builder, list builder, and other complicated nested structs. Cool. Now let's get to something useful. Let's read and write some data. The Go Arrow and Parquet libraries support Parquet, they support CSV. It also supports JSON and a bunch of other formats that you can read and write, directly converting the arrow arrays and data to and from. So, for this little example, I grabbed the movies dataset from Kaggle and decided, okay, let's build a small little pipeline to stream data from a CSV, transform a column, then write a Parquet file out. We're going to benefit here from Go's concurrency primitives and using channels to stream this and be very efficient with how we're passing things around. And the benefit, remember again, is that the array data and the arrow record batches, I'm not causing copies here. I'm going to just pass a pointer around, basically. Most of the columns are very simple. They're just, oh, this is a bool column, this is an int column. Cool, we're happy. There's a couple columns in the data set that is a string column, but the strings are JSON. So what we want to do in our little streaming example is you want to take those JSON columns and then convert them to an actual nested list column so that we have an easier time processing or doing whatever on them. And then we can write them out as an actual list column in the Parquet and get the benefits of having that nested list column. So, how do we read CSV data with Arrow? Well, recently, I actually added it specifically because of this talk. I added an inferring reader. Until that was added, which will go out with Arrow v10 in a couple weeks, you have to specify the full schema that you're going to read when you create the CSV.new reader. With the addition of this inferring reader, it will actually attempt to infer the schema from the list of headings, and it will attempt to detect the types you're using. You can also pass it options to tell it what values should it consider to be nulls. Is there a header line? You can also pass it, if you look at the documentation, you'll see that there's options you can pass. Say, you can tell it to skip some columns and only include certain columns. You can even tell it for some columns, this is the type to use. And for other columns, infer the type for me. All of those things are available and will come out with Arrow v10 in a couple weeks. Otherwise, you can just use CSV.new reader. If you know your schema beforehand, you can just pass the schema and create the schema and use it and pass it. Then you can see the reader itself just has a .next and a .record function. .next will return false when there's no more records. And one of the options you can pass the CSV reader is you can tell it how large of a chunk to read. How many rows to consider one record batch. The default, if you don't tell it to do anything, is one row is one record batch. You can pass it a 0 and it'll take the whole file as one record batch, or you can pass whatever number you want and it'll say this many rows makes a record batch. And then every time you call .next, it reads that much. In this case, we're going to read each record. We're going to retain it because we're passing the ownership off. And then we're going to pass it into a channel. And then notice that we also, and so we have our reader, we have our next, we have record retain, and we check if there's any errors at the end of our loop. And we do all this inside of a Go func, so that we done asynchronously, and so that whatever is reading the other side of that channel can collect our stream of record batches. So let's manipulate our column now. And I'm going to walk through this here, and I'm going to go through on slides. So, the column that we're talking about that I mentioned is a JSON string. Here's an example of one value in that column. So we're going to make a list builder. Now we know that to make a list, we're going to need a list of structs. Not too bad. You have a list of structs. So we make our struct type, define it, make our builder, and defer release. Builders are reusable. Whenever you call .newArray on the builder, it takes the memory allocated for the array, groups it together to make your array, and then the builder is ready to make a new array. You can just start appending again to make another array. So we can make one builder and then just keep using it in our loop. So we're going to do a range over the channel so we can get all of our record batches. We're going to pre-reserve space in the builder so that pre-allocates stuff for us. And we're going to grab the column that we wanted to use. All the columns that we're not touching, we don't have to touch. And we're not going to copy them either. So, if the value of that index is null, then just append a null to our builder, go on the next, cool. If it's not null, there's some red things I need to do, because if you'll remember from that slide, it was using single quotes instead of double quotes, and JSON spec requires double quotes, and Go's JSON reader follows spec, so I had to play with that. Don't worry about it, but data cleaning is fun, and anyone knows that. Yep. Anyways, you'll see that I just call unmarshalled JSON. All of the builders have an unmarshalled JSON method. They're JSON unmarshallers. If you have a JSON string, you can unmarshal it into a builder, and it will appropriately append the values. So I just append those values and go to the next iteration to do that in a loop. And then on the bottom, you can see I get the existing columns from the record batch. I release column 3 that I don't want, and I replace it with my new column of the struct list column array, which means I did not have to copy the existing columns that I'm not touching. They stay as they are. Because remember, a record batch is just a collection of columns of the same length. So, we make our new record. In this case, if I haven't already figured out what my output schema is, I make my new output schema. And you can see I make a new record, passing it the schema, a slice of columns, the number of rows. You can also give it -1, and it will infer the size of the record batch for you by just checking the length of all the columns and make sure that they all have the same length. But if you know the length of your record batch, you can just set it from the start. It's nice and easy. And then I release the record that I read from off the channel, because remember we did a retain before we put it on the channel. So we release it now that we're done with it here. Now we can improve this. Instead of just having one Go routine reading the CSV and one Go routine reading the stream of record batches, Go has the concurrency primitives that make it really easy that we can just make a wait group, have however many workers we want, and have all of those workers reading the record batches as they come in, modifying them, manipulating them as we want, and tossing the resulting record batch on your channel. Allowing you to really easily parallelize that whole transformation step that we just showed you. So far, we have our CSV data. In this case, we're getting our record stream, but you can replace that with any record stream, any source that's giving you a stream of record batches through a channel. Whether you're reading a Parquet file, whether you're generating them in code, whether you're reading whatever, any record stream will work that you're just passing records through a channel. Then we have one or more workers that are reading from that channel and manipulating the records. Then we pass it off all down to another channel where we're going to now write our Parquet file. So we make our file, grab the first record because we don't know what the schema is yet. We're not going to assume that we know the schema beforehand. We're going to assume that all of them will have the same schema. Otherwise, things get a little hairy, but that's something for another talk. And then we have a whole bunch of options. Parquet has so many options. Here's a smattering of them, but there's more. Read the documentation, they're all there. But you can see here, I can set a default compression and then override that for one or more columns. I can set the default whether or not to use dictionary encoding and then override that for a column where I believe it might make sense to add dictionary encoding in the Parquet file. You can control the data page version, the Parquet version, so on and so forth. But notice that we're calling PQ-Arrow new file writer and passing it that schema. It's going to automatically convert the Arrow schema to a Parquet schema for you. And if there's metadata in your Arrow schema, it will propagate it over. There's also an option for you to be able to store the Arrow schema as metadata in the Parquet file, so that later when you're reading back out from the Parquet file, it can more easily determine how to do the conversion back to Arrow from the Parquet, since not all the types line up perfectly. So on and so forth. And then you can see all we do is we loop over the channel, is write each record to the Parquet file, the writer, and we had to defer close when we're done, and that's it. It wrote the file. The CSV in the Parquet file follow the interfaces readers and writers use the io.reader, io.writer interfaces, which means your files could be wherever you want them to be, and it will work as long as you can get an io.reader to work with it. So you can use the S3 library, and that exists at AWS's S3 library. In io.reader, pass it and read a Parquet file from S3, or HDFS, or ADLS. As long as you have a reader at and seeker for the Parquet, or for CSV, you only just need reader and writer. Remember, taking advantage of Go's interface system there, where we don't have to package this whole file system thing with the Go Arrow libraries. You can just leverage what exists. If you're talking about going between processes or between interactions, above and beyond just our little pipeline that we just did, you've got the Arrow IPC format, which is an efficient way to communicate streams of record batches between processes. And then building on that, you've got Arrow Flight RPC protocol and you got Arrow Flight SQL. Both are designed for high performant communications and operating between various systems. What else can you do with the Go Arrow libraries? Well, Arrow has a define C data API so that you could use CGO, take your data in Arrow, pull it in, then you can export it to a header struct defined in your SC, and you can just pass the pointer to a C library that can then manipulate and use the data without having to copy it, and vice versa. What can you do with that? Well, you could write a Python module. You could take data that comes from Python, export it to the C API, pass it to a Go Arrow function that can then read and manipulate and operate on that memory without having to copy it, and then send it back. Or vice versa, you could call a Python struct, or a C++ library, or Rust, or anything that exposes an extra in C. You can build your data pipelines. You can build CLI utilities. Remember that Arrow is polyglot. You've got libraries in so many different languages. You can write a distributed Arrow flight service, and clients already exist in all those languages. The Go Arrow library already provides a server and client implementation for Arrow Flight and Arrow Flight SQL. So if you need to interact with something that exposes well as interfaces, client's right there for you. If you want to make a Flight or Flight SQL server, it's all right there for you. It's just gRPC, and you implement some functions. It's all right there. Read documentation, reach out to me for assistance. I'll help out. Whole 9 yards. So, the last thing I'll say is a not so subtle, shameless plug of my book. My book on Arrow, like I said, has examples and setups for Spark and Jupyter, and the examples are in C++, Python, and Go. There's a corresponding GitHub repo for the book that has all of the code in the book on the GitHub repo and instructions on how to use it. So, once again, if you do get my book, please give me a review or tweet about it or something. Help me get more people to get the book, because I think it's a really great resource, and is still currently the only book on Apache Arrow that exists. And so if you are learning about Apache Arrow or just want a resource or anything in those terms, the book is very helpful. They also have more examples, which is always great. With that, Q&A. Does anyone have any questions? Yes.
On slide 7, you had an example of who are the outsource immutable.
Yes.
Who are those? How did you come up with an example? Nope. Well, I said. Well, get on out.
Well, you see that there's the location column.
That's all.
So this is the location column.
Anyway, for a serious question, I know Melopate of any query engine written in Go. Arrow query engine.
So I'm not aware of any full Arrow query engine that already exists. I know that there is one that is being built that is leveraging Arrow, FrostDB, or Arctic. I forget, they recently changed the name. Polars. There's an AI infrastructure ML group, Spice AI, using Go and the Go Arrow and Parquet libraries. To correspond, that the C++ library has Acero, which is an Arrow native query execution engine. I'm currently writing equivalent functionality in the Go Arrow libraries. With the release of V10, there is high-performance functions for casting between different Arrow arrays and types, and for filtering and taking Arrow arrays or record batches or tables will be released with a compute library in Arrow V10 for the Go. And my hope is to eventually implement more functionality in there, to have like a rudimentary query engine written in Go, high performance, for making everything work, leveraging SIMD where I can, whole 9 yards. Yes.
So we're doing distributed arrow file generation in HBase and custom coprocessors.
Mm-hmm.
And then we're pushing that data out into a web tier. And in order to optimize it for our UI, because we're doing more time series style analysis, we need to sort things by our day column. But when you have multiple arrow files coming back and you're trying to combine them together, merging the dictionaries can be kind of a problem. Do we have recommendations?
So, I mean, merging the dictionaries can be a problem if you're using the dictionary arrays in Arrow. You can use you can use non-dictionary encoded arrays, but when you try to merge them like that, so what are you guys writing it in?
It's Java and then JavaScript.
All right. I don't know offhand on the JavaScript other than trying to just write the merging stuff yourself there. On the Java side, you could use JNI to call into the C++ Arrow query engine, which would be able to do that for you because it's already implemented. The C++ Arrow compute engine already has the functionality that you're asking for to provide like a streaming execution engine to say, I want to sort these as they come in. And you could use JNI to call that as an idea. You can leverage the fact that the CData API allows you to pass the data back and forth without having to copy it. As long as you're in the same process, you can just share the pointers.
Right.
So like if you're able and willing to go that route, I'd highly suggest taking a look at that. Otherwise, you're pretty much going to have to write your own algorithm to do it.
That's why we have it yet.
I would highly recommend taking a look at it, but potentially leveraging, in your case, JNI and the Arrow C++ library to pass around and use Arrow. Yeah.
Also, like the Parquet architecture, there's some. So they're always true. It's you. In other words, it opts in that you can show like in memory.
Yeah. The default allocator, like that when you saw that memory.default allocator, that default allocator is just going to use Go's make byte slice. It's not using Go by default at all. So everything that you saw will work without needing Go. No. You can add that if you want. There is built into the Arrow library, there is a tab you can set when building that will enable linking against the Arrow C++ library and then using the Arrow C++ is memory allocator to allocate your memory as an allocator. That does exist in there, but is not required. Everything will work in pure Go, as you saw there, without needing anything. Several of the underlying performance benefits that gets are achieved using some lower level assembly stuff that are done with C2Go ASM. But if you're unsure or wary of using that, you can use the tag no ASM, and everything will fall back to pure Go implementations. Or if it's just not one of the ones that we already built into there, it'll fall back to pure Go. Currently the SIMD optimizations for most of the stuff will exist in Parquet and the Arrow library for AMD64, ARM64, and sometimes we have some PowerPC things on some of them. We'll take advantage of Neon if it's available. Otherwise, it'll fall back to pure Go.
Thank you. And this could you just explain the Venice?
So I mean, the default memory manager, you're using Go's memory allocation, but one of the advantages you can do, say, if you're using, you can write an allocator that uses sync.pool buffer, so you can pool your buffers and reuse them. That's one example you could use. That's why it's an interface, so that anyone could add or use the allocators. Because we've seen in some projects like CockroachDB written in Go, they did their own memory allocations in malloc, and because when you get to that certain level of performance that's necessary, sometimes it pays to just bypass the garbage collector in some cases. So you could use the allocator interface to make your own allocator that implements allocate, reallocate free, and just allocates it as one slab of malloc memory that it pulls from and does stuff with, or uses JMalloc under the hood, and bypass the garbage collecting entirely. For 90% of use cases, the default allocator will be all you need.
So this is more like an Arrow question. Show me how with the manipulation bros with being at that first. Is there an approach for joiners as well?
In the C++ Arrow library, it is implemented already. Joins are there and streaming joins and hash joins and all that stuff do exist and already implemented in the C++ library. I plan on eventually adding them to the Go library, but that's a longer term goal. But but they are implemented, and wherever possible, they try to take advantage of the SIMD as much as they can when they're with the implementation.
Are there documentation about that? I'm just curious about the approach, how these to be the design calendar format during the walls.
Why? Well, I mean, the Arrow data is all columnar, and so they're just going to hold like collections of the buffers, and then build up the new ones as they go. Because an arrow array is considered immutable. You know, we have one arrow array is considered immutable. So that allows you to make assumptions as you're operating on it, and you just build up the new joined version. You know, which also the idea is if you can keep the data in the same order potentially, if it's possible, then you just slap the columns that don't change next to them and only have to rebuild the columns that are changing and with the join and things like that. So I highly recommend it if you're really curious, take a look at the code. It's on the Apache repo.
Thank you.
Bro. I think that's all the time I had, all right?
If you want to continue the discussion, we'll just go ahead afterward. Thanks, Matt.
If you find me in the hallway at all, you know, I have several copies. I'm going to have one with me every day. So find me in the hallway, talk, chat. Maybe I'll give you a copy of my book.